Okay, so now we're going to do some math. And what is our goal here? Our goal here is to take two half reactions. Now, remember that when I take these metals in the table of standard reduction potentials, it's all reduction. You notice that. And then here are all the potentials. But when I combine two of these, one's going to be a reduction, one's going to be an oxidation, so we'll end up flipping it. Now, this is very important. Remember how if I had an equation like this, let's say I had H2O2 decomposes into water and oxygen, all right? If I had something like this, and I have had a delta H of some value, and I multiplied this by 2, remember I multiplied this by 2 also, didn't I? And then I would add them up. This is not the case with reduction potentials, and I'm going to say it over and over and over again. When we are adjusting for stoichiometry, by what? By using the number of electrons to do that. These will remain the same. So let's work the first problem and I'll show you what I mean. So I'm going to move this over because I'm trying to find more room because I'm going to need more room to work these. Okay, so it says use the data in the table above to calculate this potential. Remember that if E cell is positive, reaction will go, I guess you could say. This must be positive. So that's what we're going to look at. All right. So the first thing we're going to do is we're going to pull out this first one, 2 silver plus copper goes to 2 silver plus copper 2 plus. All right. So let's pull out the two equations. 2 silver plus 2 electrons gives, 2 silver. And this one, if I look up here, now notice that this is 2 times everything. This is 1 times everything. It doesn't matter. Even though I have multiplied all of this by 2 compared to this, my E is still 0.80. Still is. All right, let's pull the copper out. Copper is going to copper 2 plus 2 electrons. Now, what I had to do with the copper, notice this one is not being reduced, it's oxidized. So in this case, we don't multiply, but we do reverse and make this negative. So this is going to be a negative 0.34. So that when I add these two together, so these cancel. 2 silver plus copper gives 2 silver plus copper 2 plus. If you remember back here, I gave you this equation. I said E for the cell is going to be E for the reduction, there it is, plus the negative, there it is. We are adding the negative of this, right? And so that value turns out to be 0.46. Okay? Let's do the next one. I'm just going to pull this out. I've got 2 aluminum. Aluminum is going to 2 aluminum 3 plus in this case 6 electrons, because I'm taking this aluminum reaction and I'm multiplying it by 2. You can see it here. So if I have 3 electrons here, I've got to have 6 electrons, right? That equals that equals a negative 1.66. So that means I've got to reverse this, because instead of having a reduction, this is the oxidation. So this is going to be a positive 1.66, right? Then I look at my tin. I've got 3, tin, 2 plus goes to 3 tin metal. There's my reduction. And I'm going to add the electrons on this side. So I'm going to go up here. Here's my 10 plus my electrons, give this. Now I've multiplied all of this by 3. So that means I have 6 electrons. But again, it doesn't matter that I've multiplied this by 3. This is still going to be a negative 0.14 volts. I add all this together. I get 2 aluminum plus 3 tin 2 plus goes to 3 tin plus 2 aluminum 3 plus, and this value turns out to be 1.52 volts. So both of these are positive, which means both of them are going to proceed, and they are thermodynamically favorable. Okay, now another type of problem that you might have is that I could give you 2 reactions, and then you are going to have to tell me how to set those up. All right, so I'm going back, I'm getting the new piece of paper. What I mean by how I'm going to get that set up is, the question is, using the 4 half reactions listed in the table above, write the balanced net ionic equation for the redox reaction that would generate the largest value. This is a great FRQ problem. Determine that value. All right, so what I'm going to do is first I'm going to look at all the magnitudes. So I've got these 4 reactions, and these definitely have the largest magnitudes. So what I want to do is I'm going to focus on these 2, but hopefully I'm going to flip this one, right? Because if I flip this one, then this plus this is going to give me the largest value. So you go to the highest magnitudes, and then we're going to flip one of them. All right. So I'm going to go with aluminum, and I want to flip this one. So I'm going to start with that one. I'm going to say aluminum solid goes to aluminum 3 plus 3 electrons. All right, so now I don't have everything given to me like I do here. I've got to do the electrons myself. All right, now that I flipped that, that's a 1.66. Okay, now I want to combine that with silver, but we're going to leave silver as it is. So I'm going to say 1 electron plus silver plus 1 goes to silver solid. And now that's going to be a plus 0.88. So here's my oxidation. Sorry, I've been kind of a little bit too far down. Here's my oxidation by flipping that. Here's my reduction. Now, before I do anything, I have got to balance. If I want to write my reaction, this is not good. And remember, we balance our redox equations by balancing the number of electrons. So I need to multiply this whole thing by 3, right? And when I do that, I get 3 electrons plus 3 Ag plus goes to 3 silver solid. But I do not multiply this by 3. Notice that I'm just going to keep it the same. I just cross all that out so I know what equations to add together. Now I've got all my electrons are good, so let's write this up here. Plus 3 Ag plus goes to 3 Ag solid plus aluminum 3 plus. And then if I add these 2 together, I add these 2 together. This is a plus 2.46. And so that is the highest value that I can get. All right, our next example of a problem, we've got problems where we're given an equation and we calculate the voltage, even if given the stoichiometry. We've been given a problem where we're asked to find the maximum voltage. And this one's a really straightforward one. I've got two half reactions. You tell me how we're going to put this together in order to get this reaction to go. Now, remember that in order for this reaction to occur, E cell must be positive, which means I can't flip this one, because remember, they're both reduction. One has to be flipped so it can be oxidation reduction. I can't flip this one because that will still be negative. So I automatically know that I'm going to flip this one. So when I flip that one, that is going to be what happens at my anode. I'm going to take chromium solid, and it's going to go to chromium 3 plus 3 electrons. Now, this would be 0.74 volts. Then I take my next one. Now let's do this here now too. We might as well. Well, let me do this first. So let's take our nickel. We're going to leave this as our reduction. Plus 2 electrons goes to Ni, and that's going to be a negative 0.28 volts. We know that no matter what we do from here on out, the value for this is going to be 0.46 volts. But we do have a problem in that if we're asked to write the equation, I've got some problems here. I'm going to have to multiply this by 2, multiply this by 3. That will make this a 6. That's a 6. 2, 2, 3, 3. That goes away. That goes away. And my final equation will be 2 Cr solid plus 3 Ni2 plus goes to 2 chromium 3 plus 3 nickel solid. This is going to be probably the type of problem that you're going to be most have to deal with. Two half reactions. Tell me the anode, tell me the cathode, make sure your stoichiometry is correct, and give the cell potential for the system. Very easy. Remember, make this positive and know which one to flip. So I'm going to stop the video here, and then the next video we're going to do 3 more really good examples of this.